All right. Welcome back, everyone, to our ATAR Notes lecture series, this time for July and this time for Chemistry 3-4. So, as part of this lecture, I'll be covering mainly organic chemistry, so that's just going to be the bulk of it. And a lot of it's going to feel like, especially for those of you who did the 1-2, it's going to feel like a lot of revision, more on the basis that this year and for this study design, the distinct changes have been that they have split up organic chemistry into its two sections. So they've split it up into the basics of organic chemistry with a little bit of reactions, or mostly reactions. And then the second part of it is all of the spectroscopy. Now, this all used to be together, and then food chemistry used to make up area of study 2. And they've sort of moved away from food chemistry. You'll find that there's not really any food chemistry anymore. There's a little bit that we'll touch on, but very minuscule compared to what there used to be. But what's really important about today's session is we're going to cover that. So we're going to be really grinding into the basics of organic chemistry, because the reality is organic chemistry it feels like it's something that's brushed over very quickly, because they sort of expect you to know the basics already. And they jump into all this advanced stuff, and if you're really struggling with the basics, you're going to fall apart. So we're going to go through the basics. We are going to go through some advanced stuff as well, for those of you who already feel really comfortable with that. We're also going to do a little quick electrolysis review, only on the basis that the last session that we did for this, so the sort of the autumn lecture series, which would have been around April, we really only just touched on electrolysis. We didn't spend a lot of time on it. Again, we're not going to spend a lot of time on it, but we are going to do a practice question where we go into a bit of detail as to how we approach that practice question. It's not a VCAR one, but it's written in a VCAR style. It's an ATAR Notes one. And I really want to approach that in how, if you were doing a VCAR exam, how you would approach that question. And then the last part of this session, which is going to go for about 20 minutes, is going to be a bit of an exam review. Why are we doing an exam review or an exam sort of approach strategy sort of discussion at this point in the year? The reality is you are halfway through the year, but you're more than halfway through year 12. And you are probably pushing 2/3 of the way through chemistry, if not more. And you have about, at the time of this lecture, I'm trying to think, you've probably got, your middle of July, you've got middle of August, middle of September, middle of October, middle of November. The exam is the start of November, so you've got 3.5 months. So realistically, you need to be studying for exams for about 2 to 2.5 months at a minimum. So you're pretty close to that point where exam study really has to start to kick in. So it's a good time of the year to start discussing how should we start to approach that. So we will discuss that as well. But let's get jumping in. Just a side note, if I keep looking up to my right, it's because my slides are on my monitor. Easy. So just a bit of a welcome. Obviously, these lectures are run by ATAR Notes and they are free, which is a really big deal. So ATAR Notes has been around for a very long time. I think about 2007 was their first sort of year of existence. I have been lecturing for ATAR Notes now for 6 years, so a very long time. And way back in, I think 2017, when I was in year 11, was the first time I attended an ATAR Notes lecture. Back then, they were obviously in person, bit of a change. COVID changed everything up. We've moved to sort of the hybrid model. But back then, I found these extremely useful and something that sort of inspired me to get involved when I finished year 12. And it's really nice to see that these things still remain free and that we still can supply these out to everyone to sort of help everyone, no matter what their situation is. As I've already discussed, we have so many free resources. So we have our study notes, we have these lectures that you're in, we have discussions, videos, etc. These are all available on the ATAR Notes website, really important. So it's really important that you sort of look at the ATAR Notes website. As you can see under there, you can see the ATAR Notes website. So really important that you sort of jump on and have a look at the ATAR Notes website when you get a chance, because you'll be able to see all the free content that we have. We also do have some paid content, and that's ATAR Notes Plus. So ATAR Notes Plus has all of our study guides, so those those hard copy study guides, they're all online and you can access them through 800 Notes Plus. Now, you can still buy the hard copy study guides. There will be links down below in the portal that you're watching this video in. You'll find those links, and there will be links that will send you to where you can buy those as a hard copy, and you're welcome to. But we also supply them now as an online sort of, it's kind of like a monthly subscription. It's kind of like Netflix, but for VCE. I know that sounds a little bit depressing to not be Netflix, but it's a really useful thing. So you can get all of that. You get all of our text guides. So especially for those of you who do English, there's a text guide for every single book. We also have these flashcards. We have a lot of, so ATAR Notes in the last couple of years has sort of taken over NEEP, which is a company that does exams. And so we have all the NEEP exams on there. The quality of those has increased drastically since taking over, and the quality of the last, I think we've had them now for about 3 or 4 years. It's really, really good. It's really good content. It's all written by sort of past students who know sort of what they're looking for and what sort of VCE and VCAR are looking for. And then we also have an AI answer bot. AI is, the topical thing of the time. I think at the time we're recording this, we're talking about sort of Apple integrating AI into all their stuff, and AI is everywhere. But really important that this is a really useful tool. The AI that is in ATAR Notes Plus has been taught AI based off all of the ATAR Notes topic tests and study guides. And so essentially it just knows everything about VCE. So it will answer your questions. It's really useful. I would highly suggest getting around it. But again, that's ATAR Notes Plus. There'll be a link down below. There's usually every single time we have a set of lectures like this in January, in April, in July, in September, we have a set of lectures like this. We always have a lecture on ATAR Notes Plus and how that sort of runs. So you're welcome to also attend that and see how you go with it. So as a little bit of a welcome, this is what we're going to cover today. So it's sort of the winter lecture series, the July lecture series, new study design, just really important. Please feel free to use the chat. So when this is premiered, so we'll do a premiere of this recording, you'll find that there'll be a chat available, and that's sort of like the bonus of coming to the premiere when it comes out. I'll be there for the 2 hours of the premiere. You can ask me any chemistry-based questions. I'll be happy to answer them. You're also welcome to sort of, what we really suggest is watching this at the same time and then asking any questions as you're going through, going, oh, hey, don't really understand this part that you discussed. Can you please explain this X, Y, Z? And I will be there to do that. The slides will be available. You'll be able to access them below. Really important, the slides are available. You just need to scroll down, click on the slides button, and the recording will be available after the premiere. I believe it's available for 7 days, and we move it to our ATAR Notes Plus, but you just need to use this exact same link. And then a bit about who I am. So as I already mentioned, I'm a bit of an oldie now. So I have been tutoring now for sort of ATAR Notes and Shoot Smart, which is our sort of secondary company, for 6 years now. So I graduated in 2018. Graduated chemistry way back then, and I've been tutoring chemistry since. I've been doing mainly class-based, but I also do one-on-one. And I'm a final year medical student, so 6 years into my degree. Took a year off to do an honours degree in the middle of it. And this will essentially be one of my last sets of lectures, which is a little bit sad, but pretty exciting to move on to the next phase of my life. But nonetheless, that's who I am. And my name is Josh. I'm hoping I introduced that to you. This will be the lecture plan. As I said, we're going to do the bulk of our sort of content in the first hour and a half. So we're going to do electrolysis review and our organic chemistry introduction. The organic chemistry introduction might go a little bit longer. That's just the reality of it. And then we'll jump into the exam approach. Now, the exam approach really should only take like 20 minutes. So if we go a little bit over in the other sections, that's okay, because the exam approach section shouldn't really take half an hour. What I really suggest as well while you're going about it, we're going to do a few practice questions as we go through. I'm limited by my ability to do a practice question on a Mac, and drawing on a PowerPoint. As you can see, if I try and draw the letter J, I've already buggered it up, but let's try and draw the letter J. Oh yeah, it's okay. That's pretty good. But nonetheless, my ability to draw on here and write on here is pretty limited. So nonetheless, there will be a lot of answers sort of popping up on the screen. But when we do practice questions, given that this is not sort of a live, it's more of a recording, I really suggest taking the time to do them. So pause the video. I'll say, look, pause, 3, 2, 1. Pause the video. Have a go at the question. See how you go with it. If you're really struggling with it, then you can just unpause and watch how I sort of explain it and how I approach the question. It's a really important, I think, at this stage of the year that you are doing these practice questions as we go through. You're not sort of sitting there and going, I'll just watch how they do it. Have a go. The only way that you're going to improve is if you keep doing it. So that's what I really suggest for these. Nonetheless, I always put these in my slides. So really important, how does the sort of study design look for our Unit 3-4? It's really important that you know how it looks. So Unit 3, you will have already been through fuels, electrochemistry, and rates and equilibria. Electrochemistry is a bit weird. It's sort of split up into the 2 area studies. You may have done it separately. A lot of students don't. You find that the first half, just the redox and galvanic cells is part of fuels, and then the electrolysis with redox and Faraday's is part of rates and equilibria. But nonetheless, a lot of people also do it as their separate topic, so I sort of like break it up. Unit 4, how does chemistry explain life? So this is what we're about to start. So experimental design is technically part of Unit 4. I know a majority of the students that I speak with regularly have already sort of done their poster practical or their practical report. That was sort of once they finished their area of study 2 for Unit 3. So once they finished rates and equilibria, they moved into it. If you haven't, that's okay. I remember when I went through year 12 and I did my chemistry, our poster was the last thing we did. We did that last. So that's experimental design. You'll talk about experimental design in that. I'm not going to go through experimental design in these lectures because experimental design is pretty sort of straightforward. There's minimal changes with this new study design. It's the same as every other science subject. So if you're doing at least one other science subject, you'll find it exactly the same. You won't have an issue. Organic chemistry, this is where we're going to discuss today. And then there's analytical chemistry. So analytical chemistry is where things have changed up a little bit. Analytical chemistry is where we will discuss spectroscopy, which was part of just organic chemistry. And then we'll also discuss some stuff like medicinal chemistry. Medicinal chemistry is definitely new. It's quite interesting. It's nice stuff to be added, especially since I've taken out food chemistry. It made sense to take out food chemistry. Food chemistry is very PE, if that's sort of a way of saying it. It's very like, it feels very PE when you're talking about things like ATP. I know we talk about photosynthesis and so forth in fuels, but it feels like very PE based and less chemistry based. And so they've sort of dosed it down and taken about 10% of it and sprinkled it throughout the other area studies. You will have noticed a little bit of it in fuels, and there's a little bit of an experiment, a little bit of it in organic chemistry we're going to talk about today. But they've made analytical chem more about the spectroscopy and then more about how we actually utilize that in everyday life and how we talk about medicinal chemistry, so medicines, which is pretty useful. It's useful stuff to be talking about. So, electrolysis review. Let's start off with a bit of a review of electrolysis because I think this is a good place to start off, and it's a good place to know sort of where we're at when we want to start moving into that exam study. So, I will be quite frank with everyone when I say I think electrolysis is the most difficult subject in VCE chemistry. I think NMR spectroscopy, which you may not have any idea what that means yet, NMR spectroscopy could arguably be the hardest, and for a lot of students it is. I found electrolysis harder, and I find that most students that I speak with find electrolysis the most difficult. Why is that? It's because electrolysis doesn't really have an endpoint. It feels like when you can ask a question about electrolysis, there's no breadth. There's no, I can't go that far. That's beyond the scope. Electrolysis kind of doesn't have a scope. And the way that they ask their questions or the way that they sort of encompass their questions can be really difficult. So that is something that we will briefly discuss when we'll do one really big practice question for this. So just to quickly point, electrolysis, really importantly, you should know all this stuff by now, but it involves the supply of an electrical energy. And essentially what happens is you do the opposite to a galvanic cell. You get that chemical energy going to electrical energy in a galvanic cell, but this time we're getting electrical energy going into chemical energy. So it's this coming backwards in an electrolytic cell. Now, what's really important is that a secondary cell encompasses all of this. So if you have a secondary cell, so if I put a 2, with an end. So if I say I've got a secondary cell, I have both a galvanic component and an electrolytic component. That is really important. It's really important to understand that a secondary cell has both chemical or both a galvanic component and a electrolytic component. Why is that important? There was a question, I think 2017 or 2018. One of the 2 years there was a question on the exam, and the question on the exam literally read, a secondary cell and a primary cell have both of what? And the answer to that, and it was a multiple choice question, the answer to that was a galvanic component or galvanic cell. And I believe it was answered super poorly. It was like guessed, pretty much. It was like a 25, 25, 25 split. So really important that you understand that your galvanic and electrolytic components are part of both a secondary and a primary. Well, your secondary has both, sorry. Your primary has just a galvanic component. So features of electrolytic cell: anode stays with oxidation, the cathode stays with reduction, or reduction occurs at the cathode and oxidation occurs at the anode. The electrons still flow anode to cathode. None of this changes. This is all the same. All of that is the same. None of that has changed. What has changed is that the anode is now positive and the cathode is now negative. So if you sort of thought of things as, happy cat, or if you thought of things as what's the saying? An oil rig cat. So an oil rig cat stays the same. But if you sort of thought of things as happy cat and then the anode's the opposite, well, you need to think about it the other way. The cat is now angry. When we talk about electrolysis, if you're electrocuting your cat, it's not going to be happy. It's going to be angry. So therefore, the cathode is now negative. It's sort of a silly way of thinking about it, but it works. Now, what species are involved? We think top right, bottom left. Now, but what's really important about this is we still, and it's really important to remember this, we still utilize the strongest oxidant and the strongest reductant. Really important. So we are still using the strongest oxidant, which I find on the left, but it's the highest up on the left. And then I use my strongest reductant, which I find lowest on the right. But now that highest on the left and that lowest on the right, I know this looks opposite in my video. I should be doing it that way because that looks the opposite in the video. The video's flipped. Now I'm interested. My left. Left was oxidant. Now, because of left and rights, God, I'm one of those people who has to put them up. Because of the left and right, so the left one here, because your left one here is highest, but it's actually going to end up lower than your reductant, which is on your right, and should be your lower, but it ends up higher. You get this, top left, bottom right, and top right, bottom left. I've got my left and rights are out the door. But that's what you get. And you end up with what is non-spontaneous chemical reaction. And this is a good way of describing it. This is now proper because you can see my left and rights. So as you can see, these are all, remember that in the electrochemical series, now, I do apologize, this is the old electrochemical series, and for some reason this has been cut off. I don't know why that's been cut off. I do apologize, that should not have been cut off. But nonetheless, in the electrochemical series, we understand that, and this is the old electrochemical series, it's exactly the same, they just removed gold and added a couple of things, but this doesn't affect this question. The electrochemical series, as you can see here, what's really important about electrochemical series is that you have this, these half equations, and all of them going to the right are reduction half equations. Why? Because the electrons are gained. Reduction involves gain. So all these are reduction. So this side is all oxidants, and this side is all reductants. And the strongest oxidants are to the top, and the strongest reductants are to the bottom. So, as you can see here, if I had copper 2+ and I had zinc solid, I'm going to get a spontaneous reaction. So it's top, left, bottom, right. But if I had magnesium 2+ and zinc, and I didn't have this here, this needs to occur non-spontaneously. I need to do electrolysis for this. For some reason, this is all being cut off, which is woeful. So give me 1 second. I am going to fix that up. Discard. You can have that screen while I fix this up. Oh no, I can't fix that up. Let's go here. Why did that do that? Let's bring that back. There we go. That looks better, doesn't it? All right, we're back. Hopefully that's better. Lovely, we're back. So, pushing through that, as you can see, so in this example, we discussed that if magnesium 2+ and zinc solid were placed in the cell setting, no reaction would occur. We're comfortable with this concept, and that's a really important concept to be comfortable with. Now, what if in this scenario, you were given our electrolytic cell are not separate? If we place magnesium 2+ and zinc in together, nothing will occur. And that's really important to understand as well. Because they won't occur spontaneously, we can put them in the same container. But once we begin to run it, magnesium solid and zinc 2+ will form, which will lead to a direct back reaction. And that's really important. With electrolysis, you can have things in the same container, and that's okay, because there's not going to be a spontaneous reaction between these two things if I put them in the same container. But once I start to run it, what am I forming? Well, if I use a different color, let's grab a different color out, which is green. Once I start running it, I form this and I form this. This looks spontaneous. So it's really important you have ways to separate things in electrolysis. And I don't believe we're going to discuss it in super detail today, but it's really important that in electrolysis, you discuss these things and you say, hey, in actual fact, I need this to occur sort of with an ability to remove the product. So if the magnesium solid forming is pulled out, that's another way that I can do it. Realistically, I'm going to have to get rid of the zinc 2+. Somehow I'm going to have to get rid of the zinc 2+. Whenever I do it, maybe I have a product in there that allows it to bind and remove the zinc 2+. Nonetheless, there are strategies to get around this, as you can see there. So let's now consider all of these products. So let's just say that we have a mixture of all of these things in our container. And once again, I do have the old electrochemical series. This is the new one, by the way. You can see here. There's very, very little changes. They've removed gold and they've added these three. So very little changes. There's not a lot. As you can see, there was gold up here. They got rid of that. Very, very minimal changes. What would be oxidized and what would be reduced? Well, let's utilize electrochemical series. You need to start highlighting what we've got. So if you highlight what we've got all of these things on the left and all of these on the right. Now, remember what I said before, that the strongest reductants are on the right, so R and R, and they're at the bottom. The strongest oxidants are on the left, and they're at the top. So reductants on the right, oxidants on the left. If we work off that theory, the copper, the Cl2, the Cl- and the O2 can be oxidized because they're both on the right. But which of these two is the most susceptible to being oxidized? Well, that's going to be the water, because the water is the strongest reductant, and therefore it's going to be oxidized into O2. On the flip side, all of these things can be reduced because they're on the left, but the Cu2+ is the strongest oxidant, so it will be reduced. So let's now do a practice question that bases itself off this sort of content. So in this scenario here, you've been given an aqueous solution of mixture of Ki, and you've been given a solution of Ca2+, Br-. So they're essentially the ions that are involved in that. It was electrolyzed using unreactive electrodes. What will occur at the anode? So start to think about, what is at the anode? So the anode is oxidation. What can go through oxidation here? So I need reductants that can go through oxidation. So I need my electrochemical series. So if I'm looking at this scenario here, I've got K+, I-. So I need to look for these things. So K+ is on the left side. It can't go through oxidation. I'm fine with that. I- can. It's up here. It can go through oxidation. And then what else have I got? I've got Ca2+ and I've got Br-. Br- can also go through it. And I can also have Ca2+, which I believe will be on the left side. Oh, it's on the left side. So these two cannot go through oxidation. These two can. So this and this. Which of these is the strongest reductant? It's this one here. This is the strongest reductant, therefore it's going to go through oxidation. Therefore, my answer here is going to be D. As you can see there, the answer is up on the screen. The answer here is D. So really important that that's how you sort of approach these questions. Now, what's really important in this question is something that I sort of didn't discuss. What about the water? These are aqueous. So what about the water? So in this question here, it's really important you identify that there is water available. So I would need to highlight my waters. There is one here and there is one here. They are the two waters I would need to highlight. When I look at this, the water is actually the strongest oxidant. So if this was asking about the cathode, I would have been talking about water. But in this case here, I'm not. So I'm talking about this side, and this water doesn't count, by the way, because there's oxygen gas with it. This is the water we're looking at. There's more water up here, but they've all got other things with it, so you wouldn't count it. There's a water all the way up here, but this one's much stronger. So I'd be working with this water. The I is still below it. The answer is still D, but it's important to understand that. Why? Because of this scenario here. If I talk about NaCl where I've heated it up and I've made it molten, it's now a liquid and it's super duper strong. When I talk about this, it's really important to understand that I no longer have water involved. I've removed water from my scenario. So my strongest oxidant has to be Na+, my strongest reductant has to be Cl-. But if I have aqueous and I have water involved, I now have these two features. And really important, if I try and do electrolysis to this, it's going to do nothing. It's going to do nada. It'll do absolutely nothing. It'll be absolutely useless. So therefore, in this case, I need to sort of consider that in these scenarios, I need to sometimes do molten. And that's something you will have discussed. As you can see, water is preferentially oxidized and reduced. And then the last part of electrolysis that I want to talk about, I'm not going to talk about secondary cells, is Faraday's laws and being comfortable with Faraday's laws. So Faraday's laws came up as part of redox in Area Study 1. It also is mainly part of electrolysis. Why? Because in electrolysis, we apply electricity. We can count, or measure is probably a better way, we can measure the voltage and the amps or the current and the time, and therefore we can go from current and time all the way through to charge, through to our moles of electrons, and then use our stoichiometry. So really important, remember that Faraday's has two laws, and the first law implies that the mass of metal is proportionate to the charge. So how do we determine charge? Really important you remember this formula. You can find this formula in your study, in your data booklet. As you can see, it's right there, but it's also really important to understand that you should know this really off by heart. The data booklet doesn't give you the units. You need to know the units. But again, how does this relate to mass? So we determine the moles of electrons by going moles of electrons equals Q divided by F. Again, super important stuff. You need to remember this. Like that is like a must. Yes, you will find that in here, but nonetheless, you need to know it. It's just something you need to know off the top of your head. You can't be stuffing around in an exam trying to remember that and find it in your book. So utilizing the electrochemical series, we can then use stoichiometry to determine the moles of the metal and then determine the mass. So if you had this here, use stoichiometry to determine the moles of Ni solid, and then mass via M equals N, so moles times your molar mass. So what's really important about this, just so you can understand, is that you've got to use ratios here. So if I'm trying to find this and I have moles of electrons, I have a 2-to-1 ratio of moles of electrons to moles of electrons to moles of Ni solid. So when I have that 2-to-1 ratio, it's really important to understand that in this 2-to-1 ratio, if I have 4 moles of electrons, I'm going to have 2 moles of nickel. So you do need to apply that. And it's super important that you get used to applying those ratios and you work with those ratios all the time. And then you can think about the pathway. The pathway goes forward and backwards. Once you do enough practice exams and practice papers, you'll find that this scenario, that this comes up a lot and it always goes forward and backwards. And so it's really important to understand how to work with it going forward and backwards. So really important you spend that time going through it and going, hey, I need to go forwards. I do need to also go backwards. So you go forward and backwards. All right, so this is what I wanted to talk about. So this has been adapted from a VCAR paper. we have gone through and done it ourselves. I've given you the new data booklet as well, the new electrochemical series. I want to update on this one. Didn't update on the other ones for some reason. I want you to have a go at this question. We are going to go through each of the parts. So there's this part, and then there is part 2, which we will discuss. So part 2 has, I think it's got like C part 1 and part 2. I want you all to pause and have a go at this. It's really important you start doing this and write down what you would write in a saccharine exam. I don't want you to write down, like 2. I want you to go like 2 volts is produced by this, whatever it is. Please have a go at this. I'll give you some time. 3, 2, 1, pause. And hopefully you had a go at that question. So let's start to talk about this question. Now, if you pause and then you come back and you're just confused, I will discuss how I'm going to approach this question. Then you can have another opportunity to pause. If you've done the question, you just follow all the way through. So a student carries out, in this scenario, the electrolysis of 1 molar solution of sodium chloride using graphite electrodes. So a couple of things from that. Graphite electrodes, these are inert. So these are not going to do anything to affect what's going on, but this will. So I have sodium chloride. I have sodium, and really important, it's 1 molar. I therefore have, and it says here, aqueous, I therefore have water and water. So I have these 4 things. And then it says, write an equation that would occur at the, I write a half equation that would occur at the cathode. And then it says 2 different gases are produced at the anode. Write equation for the 2 half equations that result in the formation of these 2 gases. So I've got equation for the half reaction that produces gas 1, equation for the half reaction that produces gas 2. So I've got 2 gases producing at the anode. And as it says here, I've got write an equation for the half equation that is the cathode. So bit of a confusing question because it's asking me about 2 half equations. And you're like, what's going on? Why do I need 2 half equations? We will discuss. So the cathode, remember the cathode is reduction, and therefore it is the oxidants. So reduction occurs, we need the oxidants, we need the strongest oxidant. Remember, the strongest oxidant is on the left, and lo and behold, we have water. So I would be literally grabbing this and writing this here. So I wouldn't be writing anything else, I'd just be writing this equation as it is. And as you can see from this, if I go to here, that's literally what I have done. So I have literally grabbed, that's a 2 by the way, I have literally grabbed this and written this down here. So as it says, we're electrolyzing NaCl with the strongest oxidant, gets reduced. So really important here is that in this scenario, the strongest oxidant is H2O. So that is my first step. Now my second step is a little bit different. So why is my second step a little bit different? So it says here that I have 2 half equations occurring. You're like, oh, what's going on there? How come I have 2? Now, I can distinctly tell you that the first one is going to be this, because it's very obvious that water is your strongest oxidant. Reductant. We are at the anode. We are going through oxidation. We are talking about reductants. Strongest reductant is lowest on the right in terms of my reductants. So therefore, this is going to be my strongest reductant. So my first equation I'm going to write out is equation for the half equation. I'm going to write that. I'm also going to write below it, just to be safe, I'm going to write oxygen is the gas produced, full stop. That's all I'm going to write underneath. So my first line here would be this equation. Remember, it's flipped, so I'm going to do 2H2O liquid goes to O2 gas plus 4H plus aqueous plus 4E minus. I'm going to write on the line below it, just here, oxygen gas is produced. Now, what is our second gas? And that is where the question comes in. These two are very close to each other. So does that alter what is going to occur? And I would say that it will. So as you can see in this question, they have put that as the first one. You can put it as the second one or the first one, doesn't really matter. What do I mean by that? So this is a concept that it used to be part of our study design way back when, and it sort of got removed, and now it's coming back into phase, and they really want you to understand it. The electrochemical series is done at SLC conditions. We understand that. SLC conditions 1 molar, what else is there? 1 molar, 25 degrees Celsius or 298 Kelvin, 100 kilopascals if you're working with a gas. Cool. Now, therefore, these things are really close. Now, if you alter the concentration, these will change. But also, there are going to be times where you're going to get some of this being produced because there's actually no water in contact. As you use up some of the water, there might be some points in time where you only have Cl- in contact with your anode. And therefore, you're going to get a little bit of Cl2. It's not a perfect world. You're not just going to get 100% O2. You're going to get a little bit of Cl2. Not a lot, but a little bit. And that's what this question wants you to recognize, that these are really close to each other, and therefore you will get a little bit of Cl2 gas. So I would put this as my second one, and I would write Cl2 gas will be produced. That is my second thing that I'm writing. Again, I want to put that in the second line. I haven't done it here, but I think it's important to have those two lines. Sort of instigates to the examiner and your sort of marker that you know what you're talking about, you're answering the question. All right, now let's move on to part C. Using the same current and electrodes, the student carries out a second electrolysis, this time of a saturated solution, approximately 6 molar. The sodium chloride instead of 1 molar solution. So we're using 6 molar instead of 1 molar. What difference, if any, would you expect at the products or expect in the products or the products formed at the cathode and the anode? So, you need to go back to your electrochemical series. It's really important here. So if I come across, really important you have your electrochemical series up. I really highly suggest having your data book up on a tab or having it in front of you. And going back to your electrochemical series and going, all right, what's going to change here? So I want you to have a go at this question. 3, 2, 1, pause. And hopefully you're back. So, really important. This question is asking you to make an assumption. So therefore, you just need to justify your assumption and justify it as you would. So in this question, what's really important is remember, we had this and we had this. Now, I want to highlight something. This is negative 0.83. This is negative 2.71. This is nearly 2 volts different, which considering there's not even 6 volts difference between the top and bottom, that's pretty significant. There's a big gap between this and between this. Now, if I come here and I get these two, there is a small gap, 0.13. It's a tiny gap. Therefore, it's really important to start understanding how the electrochemical series works. The smaller the gap, the closer they are to each other in terms of their properties. The closer they are, that if you change some of the properties of SLC, you may get a flipping of the two in the chemical series. So the cathode, remember that the cathode was our H2O or Na+. These are too far away, way too far away. This is not going to overtake this just because it's got a lot more of it. Just because there's a lot more of it isn't going to make it stronger. It's too far away. So you know what I'm going to write here? No difference. I'm still going to have H2 gas / OH ions produced. Full stop. So by saying that there's no difference, I'm also really importantly telling to the examiner that I'm still going to get the same thing produced. And it's really important that I need to say what I'm being produced. But at my anode, I'm going to get a difference. I'm going to say Cl2 gas produced with little to no O2. Now, do I need to explain this? I think it looks good if you explain it. Yes, it's a 1 mark question, but I think it looks good if you explain it. And just say that according to the electrochemical series which occurs at SLC, Cl- and 2H2 liquid are quite close to each other and have a minimal electropotential difference. Therefore, by increasing the concentration of the Cl-, I will find that the Cl- will likely become a stronger reductant, and therefore I will get more Cl2 gas produced. Full stop. Writing something like that just justifies to the examiner that you know what's going on. You are switched on. You know what you're talking about. You are going to definitely sit in their good books and get a better mark. So really important, always try and explain what you're doing. Sometimes you don't need to go over the top, but there are times where it's good to explain. Like in this first part, there's no need to explain, but the second part, there probably is. So that's just my point there. So that there is electrolysis. I'm going to leave electrolysis there. I just wanted to go through that one question And that's a really quick review of electrolysis. Hopefully you're all feeling a little bit more comfortable with it. Let's jump into some organic chemistry. If you need to take a break, let me have a look. I'm just trying to look, how long are we into this lecture? We're 40 minutes into this lecture, so we're doing good time. So this will take about an hour. And as I said, if you need a little break, go take a little break. We will punch on. So let's talk about organic chemistry. Now, when I talk about organic chemistry, I'm not going to talk about the basics of carbon and the 4 bonds and yada, yada, yada. What am I going to talk about? I'm going to talk about how we go about naming things. Why? Because naming things is probably the most important skill, and it's become a lot more difficult as part of this sort of moving into year 12. Moving into 3-4, it becomes extensively more difficult, and it becomes extensively more like to the point and detailed, and I'm trying to think of the exact word, but you need to be precise. Like the examiners and your SAC markers are going to be nitpicky about little things, and you need to be onto it. Your attention to detail needs to be really high here. The reality is you can't get away with simple little errors like forgetting a comma or forgetting a dash. It's wrong. You need to be really nitpicky here. So let's talk about how I approach nomenclature. So nomenclature, again, fancy word for naming things. Really important. This is how I approach nomenclature. You don't necessarily have to take this approach, but this is how I approach it. And I would highly suggest this is how I've taught it to all my students over the past, 6 years, and it's sat them well. So how would I approach this? So my first step here is I'm always going to identify the longest chain. And it's really important. That's the first thing I'm going to do. I'm going to name it appropriately, meth, eth, prop, whatever it is. I'm then going to identify the homologous series. Identify the homologous series next is really important. Why? Because then it can sort of set up the rest of what you're doing. So you have your ane, your ene, or your ine. You just number off your chain, figuring out where it should be. You obviously haven't done your functional groups yet, but we'll figure that out next. Then I go through and identify my functional groups. I need to determine whether I'm going to need a prefix or a suffix. That's really going to determine how I then go and name things. I then count the carbons from the highest priority end to the lowest priority end, and I number appropriately. And then I ensure there's a few rules met. Now, I should have probably put this down here because it should really be in the rules, but we'll talk about it now. Really important. When you are writing out the name of something, if you have a number, so 2-methyl, it goes 2-methyl. Really important. Now, if I have 2 of something, so let's say I've got 2 side chains, and I've got a methyl group at the 2nd carbon, and I've got a methyl group at the 3rd carbon. And I know that I'm going to have to do dimethyl. But the 2 and the 3, there needs to be a comma between the 2. It needs to go 2, 3 dash dimethyl. Really important. Commas separate numbers. Really important. You must have commas between numbers. You can't just write 2, 3 or 2-3. That's not right. It must be 2, 3. Then you put a dash between the 3 and the word. So letters and words, dashes between them. Letters and numbers, dash between them. Numbers and numbers, commas between them. Really important. Then you need to ensure there's a few rules that are met. So you need to ensure there are no spaces in your word. The only things that accept spaces are like if you're doing a carboxylic acid, so it's an oic acid, an ester where you've got an ill OA, you're going to have gaps there. There's spaces there. That's acceptable. No other point is it acceptable. If you're doing 2-chloro, 3-bromo, 2-methyl pentane, there was like 5 words in that. You read that as like 2-chloro, 3-bromo, or 3-fluoro, 2-methyl pentane. I read that as like, there's like 7 words there, but there is to be no gaps. The dashes don't count as spaces. There must be like 2-chloro, dash, 3-fluoro, dash, 2-methyl pentane. No space between the methyl and pentane. It all there must be no spaces in that entire thing. It must all be like written as one word. Duplicates of functional groups. You should know this from last year, but if you don't, if you have two of the same functional groups, you have 2 chlorines, you need to do di. If you have 3, you need to do tri. You're never going to have 4. I've never seen one come up in an exam or a SAC. I've seen them come up in like company ones that are trying to make themselves a bit harder than what they need to be. Never seen it come up in a VCAR paper. And then this is a rule we're going to talk about because this is a rule that lots of students sort of fail to learn or it's not taught. Multiple prefixes. If you have multiple prefixes, so you have multiple things at the front of the word. So you have chloro and you have fluoro. Really important that they are alphabetical order. So let's say that the fluoro in this case is on the first carbon and the chloro is on the third carbon. They're the same priority, so it's a bit hard to sort of discuss. But let's say that you've got fluoro on your first one, you've got chloro on your third one. It would make sense that you do 1 fluoro, 3 chloro, because it reads 1 then 3. It's actually wrong. You need to do it in alphabetical order. It has to be in alphabetical order. So it has to go chloro, then fluoro, because C comes before F in the alphabet. Now, if you've got a di or a tri on something, like you've got di-fluoro, the di doesn't count. You still go off the F. Or dichloro, you still go off the C. Dimethyl, you still go off the M. You don't count the di and the tri as part of your alphabet. Really important. But multiple prefixes must be in alphabetical order. Now you might say to me, what about multiple suffixes? You don't have multiple suffixes. There's only ever one suffix. You can only have one suffix. That's why some things have both a prefix and a suffix way of writing. The suffix is always like you want to do a suffix. The suffix, if you can do a suffix, you do it. But if it's not available because you've got a carboxylic acid, so you've already got an oic acid, you must then do the prefix. And if you have multiple prefixes, because you can have multiple prefixes, they must be, when they're written out, when they're put on the page, they must be in alphabetical order. And we will discuss that. So as you can see here, don't know why that number's meant to pop up second. As you can see here, first step, longest chain, you need to name down to 10. So this is a distinct change with this study design. It used to be to 8 and now it's to 10. Really doesn't change much. You just need non and dec. You should know up to oct as is. They're pretty straightforward anyway, other than meth, eth, and other than these first 4, these are all like the shapes of their like pentagon, hexagon, heptagon, octagon, nonagon, decagon. So think back to your sort of year 7, like what would be geometry and shapes. So realistically, you're just going back to there. But nonetheless, you do need to know these off the top of your head. That's reality. Bit annoying that you have to know off the top of your head, but that's what it is. Every student has gone through this exact same thing. As you can see here, here's the example of how they can be drawn out. So everything can be drawn out as a semi-structural, a skeletal, or a structural. Really important you understand the difference in that wording. Semi-structural means like this. You like write CH3, CH2, CH2, CH3. You are writing it out. You're essentially like writing it out without writing the name. Skeletal, you may not have done a lot of this in year 11. It is vital in year 12. You must know how to do skeletal. Now, really important, why is this pent? Why is this 5? Because each corner and end point is a carbon. Unless, so if I did this here and I put an OH here, that there is ethanol. Why is that ethanol and not propanol, you might say to me? Because this is a carbon. We're happy with that. This is a carbon. It's an endpoint. This is not a carbon. Why? Because I've written something out. I've put something there. Now, if I'd just drawn this, then that's propane. Now, if I wanted to make propanol, I need to add another line and write OH. That is propane. So really important. Each of the ends are carbons unless something is written there. This, ethanol. How do I draw methane, which is just one carbon? To be honest with you, I have no idea, and I don't think you do. There's no need to use the skeletal structure of something like methane. But nonetheless, really important to understand how skeletal structures work. They just don't draw in the hydrogens. Now, what if I had chloropropane, or like 2-chloropropane? Well, I would do it like this. So I have that, and then I draw another line off here, and I go Cl. So that's essentially saying that I have propane, because this is a carbon, this is a carbon, and this is the carbon, and that's my longest chain. They're all single bonds, and then I've got a chloro coming off the second one. So you do have to draw them coming off. Looks a bit weird, but that's how it works. So skeletal structure is really important. So that's the first part. Now we move on to, let's change colors. I've been using this color for ages. Let's use purple. Use purple. Homologous series. So the homologous series, again, pretty straightforward. You should know this stuff from year 11 or unit 1, 2. Alkanes, alkenes, and alkynes. Know your general formula. I don't think I need to talk about this too much. Then we go to functional groups. So there's a whole bunch of functional groups you need to know. You need to know all of these functional groups for year 12. Now, you need to know more about these functional groups than on these pages. You need to know primary versus secondary versus tertiary alcohols. I think we will talk about them. I did put a slide in for them. You need to know, why is a ketone in the middle? Why is an aldehyde on the end? Carboxylic acids, what do they form from? What do I do to form them? Esters, what do they form from? What do I do to form them? Remember where to break esters. Remember that this oxygen, which bonds the two, is involved with the OH, so the alcohol, and then this double bonded oxygen is involved with the carboxylic acid. So remember, it's a condensation reaction. Remember, you lose water, therefore an OH goes here, and you have a H go here. So remember, condensation reactions and where you break your esters, your amines, your amides. These in the past have distinctly been, you need to be able to observe them, but you don't need to know how to name them. They've sort of changed that. Same with ketones and aldehydes. They used to say you need to know how to observe them. You don't really need to know how to name them. That sort of changed. You do need to know how to name them now. So important that you do. These are all the different ones. Amides, we won't talk about as much today. These are part of proteins, really important. This bond here, if I change this to a carbon, if I change that to a carbon and then make that a chain here, that bond there would be called a peptide bond. And it's part of proteins, so you'll talk about this a lot more. Amides are quite important. So, nonetheless, you also need to know benzenes. Benzenes are in themselves a sort of a pseudo-functional group. You don't really need to know how to name things that have benzene rings in them because it's a bit complex, but benzene rings are important and you do need to know them. They're a really special hydrocarbon. Why is that? Every single one of these has one hydrogen coming off it. Every single one. So 1, 1, 1, 1, 1. So every single one has 3 carbons coming off it. What's really important is these bonds are not stable. These bonds actually move. So notice how these are, like if I put this as bond 1, notice how bond 1 has now become a single bond and this bond has moved to the right. And then if I go back, it's moved back to the left. It's moved back to bond 1. That's because these bonds are always moving. They're in that 3, so they can never be next to each other. They always have to have a gap between them. But they're moving thousands of times a second if you've got a benzene ring. So we say that the average bond number is like 1.5 because the electrons here are delocalized, a bit like our sort of sea of delocalized electrons in our metals that we talked about last year. Essentially what's happening here is these bonds are never consistent. They're moving from one to the other. And that's why you'll find a lot of people draw a benzene ring like this, because it sort of just instigates that the bonds are always moving. You do need to specifically know this molecule. You do need to specifically know that the bonds are always moving and that it's a C6H6. It's just important that you do know this stuff. And that's how a benzene is drawn. You can draw it out with the circle. You can draw it out as one of these two. It doesn't really matter. I'm not overly phased either way. You're welcome to draw it either way. But super important, you know how to do it. Each of these points is a carbon, so you have 6 carbons. It's in a chain. Cool. The other functional group, which is sort of like, again, a pseudo-functional group, is side chains. So alkyl groups is what we call them, but they are essentially just side chains. So if you've got a longest chain, so you've got 1, 2, 3, 4, and 5, and then all of a sudden you've got, coming off here, you've got an extra carbon. So essentially, this is your longest chain, but you've got an extra carbon here. That is an alkyl group. Now, depending on the length of this side chain is what you name it. So if the branch is 1 carbon long, it's a methyl group. If it's 2 carbons long, it's an ethyl group. Sounds a bit like a band, methyl ethyl. I'm pretty sure this is where they actually got their name. But nonetheless, methyl groups and ethyl groups are important. You do need to know how to name them. They do come up. As you can see here, this is an example, 2-methylbutane. Now, some of you may say to me, which of these is the methyl group? Is it this one or is it this one? Because essentially, I can name that as my longest chain, but I can also name that as my longest chain. If I'm being honest with you, either of them. Doesn't matter. Just pick one. Yeah, it doesn't matter. The only scenario where you will specifically pick one is if maybe there's a chlorine here. There's a chlorine here. I'm going to take this as my longest chain. I'm not going to take the other one because it's just going to simplify answering this question and naming this molecule. If I have to put a functional group on a side chain, it becomes really messy and it's not something VCE expects of you at this time. So important, if there is a functional group, I'd take that as my longest chain. If there's not, it doesn't matter, just choose one. Because they've both got the exact same name, it doesn't matter which one you choose. But as you can see here, 2-methylbutane is the name because the longest chain is 4, so it's but, they're all single bonds, it's ane. My functional group is a methyl group. It's found on my second carbon because this will be my second carbon no matter what. Therefore I have 2-methylbutane, all one word with a dash between my number and my letter. Very cool. I'm very happy with that. Then we have alcohols. So alcohols, really importantly, as I said, you need to be able to name secondary, tertiary, primary, secondary, tertiary. There is far more to this. There is far more to the reactivity and what is important about these. We're not going to discuss it today. Again, we're not going to go into super detail of all these little points today. We're just going to discuss some of the basics. But really important, alcohols can be broken into primary, secondary, and tertiary. And that's a super important thing to understand. Now, why? Well, if I take this carbon, and I take this carbon, and I take this carbon. So each of these carbons are attached to the alcohol group, or the OH, the hydroxide group. This carbon has one carbon attached off it. This carbon has 2 carbons attached off it. And then, just coming back, this carbon, where is it? Has this many coming off it. So, really important. I have 3 scenarios here. I have one where I've got 1, I've got one where I've got 2, and I've got one where I've got 3. And notice the naming. I have primary, secondary, tertiary. Makes sense. Primary has 1 carbon coming off it. Secondary has 2 carbons coming off it. Tertiary has 3 carbons coming off it. It just makes sense. So really important. That is how that works there. The primary and secondaries are far more reactive than the tertiaries. They become less reactive as they go up the chain, essentially. As you can see there, I make it look all nice and do it properly. So let me get rid of all this so you can see it in its nice glory of what I actually went and did before this and put some animations in and made it look nice, and then I went and drew over the top of it and ruined it. But nonetheless, all right, let's choose another color. Let's go blue. As you can see there, that's what we're doing. So what about if we have 2 functional groups? As I said before, this is where things get a little bit difficult. So when we have 2 functional groups, we need to know how to name compounds with up to 2 different functional groups. To be honest, we actually need to name things up to 3 functional groups. That's what comes up now. So how do we name something with 2 different functional groups? 2 suffixes, you can't do 2 suffixes. So as I said, you need to know your priorities. Now, this lacks your alkyl groups. Your alkyl groups fall in between here, but it's not really a big deal because alkyl groups usually try and keep them separate. But nonetheless, this is your priority table. So when you have a molecule and you need to name it and it's got multiple things, this is about numbering priority. This is not about naming priority. Remember, naming priority is all about alphabetical order. This is sort of about naming priority in terms of the highest priority will always get the suffix first. So the higher the priority on this, the more likely you are to get the suffix. However, when it comes to naming multiple prefixes, remember that is alphabetical order. Alphabetical, alphabetical, alphabetical. However, when we are numbering, so we're numbering our carbons, we are numbering according to this priority group. We are numbering accordingly from highest priority to lowest priority. Carboxylic acid has to be at the end of a molecule. We know that. It has to be at the end. If I go back. Where is my... Yeah. So remember, carboxylic acid has to be at the end. Has to be all the way back here. So given that it has to be at the end, usually it just makes it easier for us chemists to give this one. And that's what we do. So we give that the highest priority. So there is a carboxylic acid, it must be a suffix of oic acid. It takes the suffix no matter what. It therefore means it is number one. That is always the first carbon. That is the first carbon of that in no matter what. Your next priority is your alcohol, then it's your amines, and your amides is usually about the same, and they usually sit in the same spot. This is amines here. And then we go to alkenes, alkynes, and then your halogen groups, so your chloro, fluoro, bromos, they are last. We do not care about them. They are last on the list. Yes, they make us slightly more reactive, but they don't really do a lot. So they end up last on our priority list no matter what. They're the lowest priority. That is the reason you only have prefixes for it. So bromo, fluoro, ido, chloro, you only have prefixes for them. You don't have any suffixes. Now, these two are an exception, obviously, an ane, because they're always going to be a suffix because it just works. It's just part of it. So don't worry about this like being there. Just think about the priority of it. So where you're numbering from. So these are pretty low on the priority group. So if you've got an ene bond at one end and a carboxylic acid at the other end, you're obviously going to number from the carboxylic acid end and then put the ene bond on, like it's at the end of the molecule. So really important. This is just in terms of talking about priorities. This is where this is pretty low on the list in terms of priority for numbering. And that's really about it for that. So that's a really good table. You should have a table like that in your summary book / workbook, whatever you work with. Really important to have something like this so you can always sort of come back to it and go, all right, let's just check where we're at. All right, so a couple of extra bits as we talked about. So this is a really good example of this alphabetical order. So in this case here, we've got a scenario where our longest chain is probably this one here. I'd say let's just take that as our longest chain. We have 1, 2, 3, 4, 5, 6. So we're working with hex. So I'm fine with that. They're all single bonds. So we're working with hexane. Now you can see the answers to the right, but I just want to go through this manually. So we've got hexane. Now I've got a methyl group, I've got a methyl group, and I've got an ethyl group. So let's talk about a couple of things here. So as you can see, this should be 3, by the way. Lol. I love how this, I've tried to make a really big deal, but I've somehow boogered it up. This is meant to be 3. This is meant to be, I can't believe I've somehow boogered that up. That's meant to be 3. Nonetheless. So when we've gone through and we have numbered off, I have the option of, wait, no, 1, 2, yeah, 3, 1, 2, 3. Yeah, so this needs to be 5. How have I buggered that up? I buggered up the numbering here, everyone. I do apologize. I was doing this the other day, and I think I just misread. I missed one of my carbons for some reason. That should be 5. So, really important. So, when I number off, just as an important thing, ethyl takes priority over methyl because it's bigger. So, ethyl will be at my, will take numbering priority. So, ethyl here is going to be your 3 rather than being 1, 2, 3, 4 and having this as 2. It's going to be 1, 2, 3, 4, 5. I don't know why I've put 4 in there. I just forgot one of the carbons unless. So, what's really important about the scenario, and less so about the numbering, I'm not worried about the numbering, so I do apologize about the numbering being wrong, but you've got hexane. Now, with your hexane, what's really important here is that you have 2 methyl groups and you have 1 ethyl group. So, dimethyl. Dimethyl reads di-methyl. It reads D. Ethyl reads E. A, B, C, D, E. So you would naturally think, as I said, dimethyl would go first, despite the fact it's numbered second. But it's actually wrong, because we work off the methyl. We don't work off the D. We don't work off that. We work off the methyl, and we work off the ethyl. E is before M in the alphabet. E, therefore, goes first. Ethyl, methyl, ethyl, methyl. Because the E is the higher sort of naming priority in terms of our alphabetical order. So E goes before M, therefore it needs to go ethyl, methyl. I do apologize about the numbering. Don't worry about the numbering here. Numbering doesn't influence it. I'm just talking about ethyl going before methyl. Really important. Despite the fact it's got a di there and D ends up before E, it doesn't matter. You go off the M and you go off the E. So E before M, therefore ethyl goes before methyl. So as it says there, you're going to work off the alphabet. You're going to do dimethyl. Dimethyl, the M, hence, will be placed after the ethyl because E is before M in the alphabet. If the same substituent is repeated on the same carbon, repeat the number. So as you can see there, 5, 5. Don't write 2-dimethyl, write 2,2-dimethyl, or as you can see here, 5,5-dimethyl. Really important. All right, let's answer some questions. So we're sort of halfway through organic, so we're on track, we're doing really well. Let's answer some questions. I want you to take a little bit of time. Each of these questions, what I'll do is I'll give you a couple of minutes, or like I'll tell you to pause. I want you to have a go at it. I want you to name the molecule, and then we will go through the name. So again, I want you to have a go at this. 3, 2, 1, pause. Hopefully you're back. All right. So again, remember these questions, we're going to go through our 5 steps. So longest chain, bute. So I'm comfortable with it being bute. I'm probably going to run out of room here, but nonetheless. I have single bonds, so ane. I'm not going to add the E because I know there's going to be a functional group. 2 functional groups. I've got 1. Carboxylic acid. That is always going to be highest priority, so that's going to be 1. 2, I have a alcohol. So this is going to be butanoic acid. Now, really important, you do not need to number oic acid. Why? Because it's always the highest priority. So it doesn't change. So therefore, it's always going to be in your first place. Therefore, there is no need to write 1 oic acid. Now, alcohol, that's ol. But in this case, I can't use ol because I've already got a suffix. So therefore, I need to use a prefix. I need to do hydroxy. So I need to go 2-hydroxy. I'm going to run out of room here just because I can't. This is terrible. Hydroxy, there you go. That actually was not too bad. 2-hydroxy butanoic acid. Really important. I've got the 2, I've got the dash. So my 5 steps. 1, longest chain, bute. Single bonds, ane. What are my functional groups? Oic acid and hydroxy. What is my numbering? Start here, 1, 2. 2-hydroxy. Have I done my dashes and my commas? I've done my dashes. Are there no spaces other than the oic acid? There's no spaces other than the oic acid. Have I done alphabetical order? I don't need to worry about alphabetical order. Cool. I've done my 5 steps. I'm comfortable with where I am. I think this is correct. This is correct. It's 2-hydroxybutanoic acid. All right. Let's jump on to the next one. Again, I want you to pause. 3, 2, 1. Have a go at naming this molecule. And hopefully you are back and you've had a go at this question. So again, longest chain, 1, 2, 3, 4, 5, 6. All right, I've got 6. So this is going to be hex. Oh, I need to give myself more room than that. I need to start doing it at the bottom so I give myself more room. Let's go green because this is green. Hex. All right, so I've got hex. I've got single bonds, so it's hexane. I'm not going to add the E yet, just in case. Hexane, I have 2 fluorine groups, so fluoro. These numbering priority are, there's no other functional group, so I number from the closest carbon, therefore it's going to be 2. So there are 2 of them, so I need to go 2, 2, dash, fluoro, hexane. Now, have I done everything right? I've got a dash, I've got a comma between my 2 numbers. I haven't done di. So always really good to go back and check and go, oh, have I done this correct? Well, I haven't done this correct. I missed the di. So what am I missing? I'm missing di. D, I. And then I need to write out my 2, 2, dash. So let's check it again. Have I done longest chain, hex? Correct. Have I done ane? Correct. Have I done fluoro? Correct. Have I done difluoro because there's 2 of them? Correct. Have I done 2, 2? I have. Have I done a dash? I have. Good. I've got the correct answer here. So it's really important you reflect on your answers. Always check your answer. Now, you actually cannot see my answer because I put it under the thing. There you go. I do apologize. I don't know why I put it under there. You should be able to see that now. So down below, you've got 2,2-difluorohexane. So really important, 2,2-difluorohexane is what you're looking for here. It's all one word, and it had 2, 2. Now, I'm going to make sure that in my next one, move that across a bit, I'm going to make sure in my next one I don't write under the camera. Apologies, everyone. All right, let's have a go at this last one. You have a skeletal structure. Have a go. Let me know how you go. 3, 2, 1, pause, and hopefully you are back. My coffee is cold. All right. In this question here, longest chain first. So usually with these, my way of doing it is drawing out each of the carbons. So 1, 2, 3, 4, 5, 6, 7. So I'm working with hept. All right, I've got 1, 2, 3, 4, 5, 6. There is a double bond here. All right, so I'm not going to write ene yet just because I need to know functional groups and priorities. Are there any other functional groups? No. Numbering priority, well, it's going to be the closest end to this. So this is 1, this is 2. So it's going to be dash 2 dash ene. Is there anything else? Is there any commas? Anything else I need? No, I've got the dashes. Cool. It's all one word. Yep. Awesome. I'm happy with this. Hept 2 ene. Hopefully you can see that. It's not under the camera. It's the other way, isn't it? It's that way. That way. That way. The camera's flipped, so it makes me feel so weird. That's my right hand. It's on the left side. Nonetheless, as you can see there, everything else is as it should be. You can see your hept 2 ene. You can see the skeletal structure. You should be fine with all of this. Awesome. All right. Quickly, let's talk about isomers because isomers are important. So isomers do come up. Now, really important, if you've got old notes from the old study design, you've got your older brother, older sister, mate or something, really important, there was a thing called stereoisomers. That has been moved to area study 4. They've split up isomers into the two area studies now. So if you're looking and you're going, why is there no stereoisomers? Why is there no superposition? It's good to talk about it in the next area study. It's quite difficult, so you're probably reading it and being confused. Don't worry about it. You'll talk about it next area study. So isomers for this area study are structural, and they're broken up into 3 distinct categories: chain, functional, positional. So structural isomers are essentially a form where the atoms in the molecule have the same molecular formula, but they bond together in different arrangements. So they're the same stuff, just different ways. So chain isomers are where the components of the main carbon chain are distinctly reordered to give rise to create a different structure with branching alkyl groups. So you go from pentane to 2-methylbutane. As you can see here, you have got C5H12, C5H12. You've got the same thing, but you've got a different molecule in terms of the chain. The chain has changed. This is not a position of something. You have changed the chain. So you've gone from pent to but with a methyl group. Really important. Positional. Positional is where you actually move something. So you've got a functional group and it changes position on the parental structure. So as you can see here, you've got pentan-1-ol to pentan-2-ol. So you've got the same stuff. You've got an alcohol that's a pent, it's 5 carbons long. It's a pentane, they're all single bonds, but your alcohol has just moved. You've moved the alcohol from the first position to the second position. That's simply all you're doing. As you can see here, same molecular structure. C5H12, C5H12 with an oxygen added to both. Same structure, everything. You've just moved the position of the functional group. Really important to understand that that is all you have done there. That's all you're going to change. Then you have your functional isomers. Now, these are a lot different. These are, all of these ones here, they usually have very similar properties and there's not a lot of difference. Maybe there's a slight difference in reactivity here because obviously you've gone from a primary to a secondary alcohol. Here you've got a side chain, so you are going to have a slight different reactivity and way that it moves around. This here is where it's functionally extremely different. You have changed your functional group. Same molecular formula, but you've got a different functional group. As you can see here, you've gone from propanoic acid, a carboxylic acid, to a ester, methyl ethanoate. This doesn't happen. You don't just get a carboxylic acid and then manipulate the exact same molecules into a methyl ethanoate, into an ester. It's not going to happen. We're just saying here that these two things have the exact same things involved. They're just functionally completely different molecules. And that's really important to understand. These are just completely different despite the fact they've got the exact same stuff involved. So super important to understand. Propanoic acid, methyl ethanoate. So unlike the last two, this is much harder to produce as molecules rarely rearrange to form new functional groups. It's not really achievable to do this. All right, let's have another question. This is a common question type. Now I've used a very simple sort of set of molecules or atoms here, but this is a high common question. This is commonly a question. So, how many structural isomers of C5H12 are possible? Have a go at this question. 3, 2, 1, pause. And hopefully you are back and you've had a go at this question. If you're struggling with this question, you've come back and you had no idea, really important tip, have a go at writing out each of the things. So write out pentane and then write out the next one and the next one. Write out all the ones that you can possibly do. I find that's the other way to do this question. So this question, the answer is B. Why is it B? Because these are the three things you can do. You can do pentane, so you can do a straight line. You can do 2-methylbutane, so you do a methyl group. Or you can do 2,2-dimethylpropane. That's the only way that you can do this. Well, the three ways that you can use these and make isomers. So in this question, the answer is B. You can make three things, and they are the three things that you can make. So as I said, best way to do these questions is to write out the three things. So write out everything that you think you can make and check that they are not the same molecule you're writing out twice. And then once you've got it, tick it off, move on. Usually a common question with this is, what about 3-methylbutane? It's the exact same as 2-methylbutane. There's only one functional group, so I'm always going to number from the closest end. Therefore, this isn't going to change. So really important. All right. Now we're going to talk about reactions. So this is the second aspect of the first area study of organic chemistry. So we've talked about different naming and organic compounds. Now we're going to talk about how do those actually react and form each other. So there are 6 main reaction types you need to know. The 6 main types are substitution, you need to know addition, you need to know oxidation, condensation, esterification, and hydrolysis. What's the next one? 6. So these are the 6 main types you need to know. You need to be able to work your way through these 6 main types. So let's discuss how you approach these. So as you can see here, just a little meme. Why is reactions useful? Well, how can you make money out of a chemistry major? So, I don't know why I count twice. All right, let's talk about substitution. So substitution is usually done with chlorine. Now, if you're going to work with chlorine, you need to have heat and UV light because chlorine is really hard to break apart. So you need to have chlorine gas, and it gets broken into chlorine and chlorine. And essentially what you do is you take your molecule, like a methane, and you add this with your heat and your UV light. Really important, this needs to be on your arrow. And you form chloromethane. You can keep doing this and form dichloromethane, trichloromethane, tetrachloromethane. You keep doing this. You're welcome to do it. You're welcome to fill out your whole molecule. Very rarely do we do that. But in this case here, it's really important. You must have heat and UV light. It's the only way that this is broken. And chlorine is the most common thing you're gonna substitute on. This is the one thing you're gonna work with the most. So in principle, substitution may occur as many times as you want. You can then produce a polyhalogenated molecule. Polyhalogenated just means that you've got more than one halogen group. As you can see here, these are all halogen groups. So you just keep adding chlorines, you're adding more halogen groups. This is the most common one that you're gonna do. As you can see, you can then go and form all these different ones, but it's really important that you know that this is random. It's going to get added to anyone. You can't really control which one's going to get added to. And it's going to, you need to use heat and UV light to add it on. Also, what's really important, Haloalkanes can also undergo substitution. So when you have a haloalkane, so as I said here, you can sort of polyhalogenate, and it's random. But it's going to take a while to get something like this from here. Why? Because most commonly, this will be broken up and it will replace the chlorine that's already there. Why? Because this is the most unstable part of this entire molecule. So it's the most likely to want to break off. So therefore, if you try and substitution reaction this again and try and get rid of one of these hydrogens, you're actually probably just going to get rid of this and then add another chlorine, because haloalkanes, so alkanes of the halogen group, are more reactive because their polar bond undergoes a bunch of different types of substitution. One such example is the formation of alcohol by substituting a hydroxyl group onto our chloro group. So as I said here, this is the most unstable. So this is the most likely to want to come off. And especially when you try and add this NaOH, or you're trying to add the OH to make an alcohol, this is 99% of the time going to be the bit that comes off. It's going to come off. It's not interested. It doesn't want to be there. So it's going to come off and you're going to get an OH group coming on. So this is the most common example. You can then go further to this and go, all right, I want to make an amine. Well, to make an amine, this is even more unstable realistically. So therefore it wants to come off and you form an amine. Now you do need to do this because this needs to be broken off and it's quite hard to get one of these to come off. But it does happen, and you therefore, as you can see, are substituting on. So any alkane that already has a functional group, that functional group is more likely to want to come off than to stay on. And that's a really important aspect of this topic. And it's really important to understand that. All right, continuing on. Addition. So addition reactions are essentially where we add things on. So substitution, we got rid of something and added something else. This is where we just add something. So we've got spare spots. This usually occurs with alkenes because you've got a double bond, which means we're unsaturated. We haven't got maximum amount of things bonded on. So therefore, if we break this bond and get rid of this, we have two spare bonds on either end to fill. As you can see there, we fill them with bromines. Now, you cannot add both bromines to one end because it's not going to work. You have to add them to both ends. So compared to alkanes, alkenes are fairly reactive due to the double bond, which is not as stable as a single bond. Unlike substitution reactions, there's no inorganic product. This occurs a lot easier. You don't really need anything here. You don't need anything on this. There are some forms that need a little bit, like chlorine does need some stuff, but it's not a big deal. You don't really need much on the arrow just because this is far more unstable and is more likely to try and attract these things on. There are three main types of addition reactions. That's a three there that you can't see under me. Three main types of addition reactions. These are the three main types you do need to know. So you've got hydrogenation. It's the addition of hydrogen. So you're adding hydrogen, you're essentially just making an alkane and alkane. Cool. This does require a catalyst. You don't need to know what it is, you just need to know that it requires a catalyst. Halogenation, so this is the addition of a halogen group. Now you can also add something like a HCl, so you can just add one if you want. So you just go, oh, I actually just want to add HCl. I just want one chlorine. You can add HCl instead of Cl2, but you can use both. It doesn't matter which one you do. This is halogenation because you're adding a halogen group. And then hydration is hydration, it reads as it is. You're adding H2O, which means you're actually adding an alcohol group to one end because OH goes on one and the H goes on the other. You do need to know this. 300 degrees, again, not necessary. You can just remember heat, but 300 degrees is one of those things that has come up in the past. But you need to know H3PO4. So if you're going from an alkene to an alcohol, it's really important that you know H2O. Is the thing that you add on, and you get an OH group here, and you get your H group. Probably this one here is the one that's added on, and therefore you've essentially hydrated this molecule, if you'd like to think it like that. It's sort of a weird way of thinking about hydration, but that's sort of how they want you to know it. So this is hydration. Then we have oxidation now we've been through addition and we've been through the substitution. Our third one was oxidation. So oxidation is redox. We're thinking about redox here. So take a step back in time, going through redox. We just went through electrolysis. So we're back on the topic, talking about oxidation reactions. So oxidation reactions occur in primary and secondary alkanols. So primary and secondary alkanols, they form ketones, aldehydes, and carboxylic acids. So oxidation, remember that oxidation involves the loss of electrons. Well, it also means the gain of oxygen and the loss of hydrogen. So this requires a really strong acidic catalyst. Really important. What are these catalysts? If I'm going through oxidation, these are going to be oxidants. So this is an oxidant and this is an oxidant. Really important to understand. So given you have these oxidants, this is what happens. If I've got a primary alcohol, I go from an alcohol to an aldehyde and pretty much instantaneously go to a carboxylic acid. This step sometimes is just skipped. VCE will sometimes just skip this step. So be aware that sometimes you will go from this to this. It'll be very obvious when they are skipping a step. Like, it's very obvious, but make sure you are aware that sometimes they will just skip the aldehyde. Why? Because the aldehyde is very commonly not, like, it's very commonly when you do this reaction in real life, it's very quickly goes from an aldehyde to a carboxylic acid. It doesn't really stay as an aldehyde for very long, so it's not really a useful thing to think about. But nonetheless, this is the first step. It does form an aldehyde first, and then it forms the carboxylic acid. But be aware sometimes this step is skipped. Now, really important. You can use either of these. Doesn't matter which one you use. You're welcome to just remember which one you want. I tend to use dichromate. I find dichromate the easiest to remember. Really importantly, secondary alcohols, they form ketones. Now, they do not form carboxylic acids. Why is that? Because it's not possible to add another bond here to do an OH. It's not possible. It's already saturated in its bonds. It cannot drop a hydrogen. There's no hydrogen to drop. So therefore, it's not possible. So this just goes to a ketone. This doesn't go any further than a ketone. So this is purely just a ketone. It doesn't go any further. So therefore, it's really important to understand that you're not going to get any further than a ketone here. You're only going to get to a ketone. So as you can see here, you get primary to your secondary. You get your primary all the way through to your carboxylic acid, but secondary only goes to a ketone. So primary goes to an aldehyde, then to a carboxylic acid. Secondary only goes to a ketone. Important stuff to remember. So here is a question here. It says here, what is the systematic name for the product of the following reaction? So as you can see here, we've got a primary, and all of these answers are oic acids. So we are skipping the aldehyde. We're not worried about the aldehyde. We are skipping the aldehyde. So have a go at this question. Tell me what you think the answer is. 3, 2, 1. Pause. And hopefully you are back. Hopefully you had time to answer that question and you sort of knew what was going on. So have a go at this. Oh no, you've already had a go at it. Don't know why I said that. All right, so in this question, you have an alcohol group here. Now this alcohol group is going to form, actually I don't think that's probably a silly way of doing it. Let's just get rid of that. This alcohol group is going to form, let's get rid of one of those. And then let's go, actually I need both of those gone. Double bonded to an oxygen. So that's what it's going to become. It's going to become an oic acid. It's still going to be 1, 2, 3, 4. It's still going to be bute. So it's still going to be 4 long. It's not going to be pent. So neither of these. So it's going to be bute, 4 long. The oic acid is going to be the highest priority. So this is going to be 1. It's always going to be the highest priority. Then this becomes 2. This becomes 3. This methyl group is now on the 3rd carbon. So the answer here is going to be D, because it's going to be 3-methyl-butanoic acid. It doesn't come up with the answer, but nonetheless. 3-methyl-butanoic acid, because you're numbering from the carboxylic acid end, and that is going to be carbon number 1, carbon number 2, carbon number 3, carbon number 4. There's 4 carbons. It's a bute rather than a pent, so that's how I wrote A and B, and it's going to be 3-methyl. Very good. So, condensation reactions. These are next. Condensation reactions, if you do biology, these should be a walk in the park. If you don't do biology, that's okay. These are still a walk in the park for everyone. So, condensation reactions, essentially, think about condensation on your window. Think about when you have a really hot shower and you've got like water dripping down the window. It's like, you think it's like steam. It's condensation because it's just different temperatures around things. And essentially, condensation is just water. And that's what a condensation reaction involves. The removal of water. As simple as that. So, when an amine group, NH3, is substituted for the OH group, the reaction conditions are the following. And as you can see there, you have taken this off, you have taken this off and you have added this to here. That's what's going on. But if you notice, you have OH and you have a H left. Well, it's 2 hydrogens and an oxygen. What's that make? It makes H2O. It makes water. So water has been removed. Water is the byproduct. When water is a byproduct, the reaction is a condensation reaction, no matter what. If water is a byproduct, it is a condensation reaction in chemistry. Really important. So in this case here, this is a condensation reaction because you've had this change from a sort of a condensation reaction to from a alcohol to an amine, but you've also had water removed, so it's a condensation reaction. There are some other examples of this, especially when you form an ester. So when you form an ester, you have water come off. That is another really common example of condensation reaction. Now, as you can see here, this is the esterification. This is also a form of condensation reaction. So esterification is sort of like a subcategory in that condensation reaction here. So the esterification reaction occurs when a carboxylic acid reacts with a primary alcohol and yields an ester. So really, really important. There's 2 things here. It requires heat. So when you're running your arrow, it requires heat. It also requires concentrated H2SO4 or liquid H2SO4. So if you write H2SO4 aqueous, you are wrong. Wrong. It's just wrong. You write H2SO4 aqueous concentrated or concentrated H2SO4 aqueous, you are correct. If you write H2SO4 liquid, you are correct. They are the only 2 acceptable things for the catalyst. Why? Because in this reaction, if we think about it in terms of, let's think about this in terms of equilibriums. If I have just aqueous H2SO4, I've got heaps of water. What's this reaction going to want to do? It's going to want to go backwards. Why would it want to go forwards if I've already got heaps of water there? So this is like taking into account our equilibrium now, and we're thinking about equilibrium reactions. This thing doesn't want to go forward if there's already water there. So you mustn't have water there. So concentrated H2SO4, even though it's got a little bit of water, it's not a lot, but H2SO4 liquid just has no water. So it's the best option. So as you can see here, H2SO4 is definitely the best option. You add your alcohol, your carboxylic acid to your alcohol, and you get this formed here. Really important. That is where you split it if you're thinking about this molecule. This is the carboxylic acid side, so you've lost this. And then this is the other side is the alcohol, and you've lost that. Now, I don't know if I go through naming, I don't. In this question here, it's a bit easy because the naming is going to be the same because this is eth and this is eth. But let's say for the sake of it, I added in a carbon here with 3 hydrogens. So I get rid of that and I add in 3. So this now becomes prop. How do I name this molecule? Well, the naming of this molecule is really important. This is now the alcohol side because I've split it here. So this is going to be prop. That's a terrible P, that's a P. Prop. Now, this is all single bonds, so it's ane. But we don't put ane, we just put il. If there was a double bond or a triple bond, you would put that in there. If it's ane, you don't. Now, you don't need, for VCE level, you're not going to need to worry about it. It's always going to be ane. They're not going to throw you a curveball here. It's just always going to be ane. So, propyl. Then here, this is eth. Now, you do need to put the ane here. So if there is a triple or a double bond, you do need to put it in, and you do need to put ane, eth, and noate. So the O8 goes on the carboxylic acid side. So the carboxylic acid here was eth, or ethanoic acid, and then your il, which goes first, is your alcohol. So we're assuming here this was propanol, because I've made it bigger to change it up. But propanol, so propyl ethanoate. Really important. Been talking too long. Sorry, everyone. So propyl ethanoate, really important. And it has water coming out. So this is your reaction here. All right. Hydrolysis. So hydrolysis is our last reaction type. Hydrolysis is just the opposite of what we just did. Hydrolysis is breaking down using water. So in this case here, if I wanted to break down an ester, I need to add the water back in. When I add the water back in, it breaks this down back into your carboxylic acid and your alcohol. Really important, you know where to draw your line again. So that's where I'm going to break it up. This is for organic reactions. We utilize this. We utilize this in esters. So if we want to break an ester down, we add water back to it. It just makes sense. Hydrolysis, hydration, you're adding water back to it. What's really important as well, and this is a really distinct way to learn, and I always go through with my class and my students sort of like a poster for reaction pathways. I think it's the best way to do it. I'm not going to go through that today, but I'm just going to go through like a mini sort of example. You can make reaction pathways out of this stuff, and you can learn from that. And this is the way VCE wants you to learn it, or VCAR wants you to learn your organic reactions. This is distinctly how they have set it out. They want you to learn it like this. They want you to know, if I start here, how do I get to there, and work through the puzzle that way. So when you're learning your reactions, yes, learn your reaction types separately, but then make up a big sort of diagram pathway poster that has all of your reactions sort of intertwining into each other. How do I get from one thing to another? And make multiple little break-offs where it goes one way, it goes another way, etc., etc. Because this is what they want you to know. And why do they want you to know it like that? Because they ask questions like that. This is from 2014, I believe. This is an older question. I haven't put new questions in here because I don't want to sort of expose new questions. So when you do the exams at the end of the year, but I think this is from 2014, I think. But nonetheless, these questions are very similar every year. You look through all of the exams, all of the organic reaction questions are extremely similar. They give you a pathway like this. And then they have reagent X, so that would be one of the questions. One of the questions would be answer compound A, compound B, compound C. This is literally what this question is going to look like. They ask you in a reaction pathway sort of position. This is how they go through these questions. So really important that you know how to go through these pathways, because these pathways come up. This is not, I'm not trying to like trick you all and scare you all and be like, oh, look, pathways, it's just an easier way. I think it is easier, but I don't think it's necessarily super easier. It's just that this is how VCAR asks their questions. And if you learn something in an approach of how VCAR asks the question, you're going to find it far less difficult to go through. And that's a really important point. So if you learn things, how VCAR is going to ask things, you're not going to have issues with going through the questions. And that's a really important point here. So that's a VCAR 2014 question. I'm not going to bother going through it. You're welcome to go through it if you'd like. You can go find the answers on the VCAR website. It's just the questions are all like worded out underneath, and I just didn't put them there. Now, what we haven't covered as a part of Area Study 1. Area Study 1 is actually pretty big. So we haven't gone through the full pathway. We went through all the reaction types, and I gave you a very small pathway, but it's really important you go through that full pathway, which I just discussed. Macromolecules is a part of this, so going through monomers and polymers, macromolecule reactions, which are all the same as those 6 reaction types. You just have to remember which distinct ones work for which. So like glucose into glycogen, or like amino acids into peptide, polypeptides, things like that. Zwitter ions is a part of this. You need to know your organic properties, so bond strength. That's distinctly something they've added in this year and we haven't sort of discussed. If you scroll through your data booklet, let me find it. Nope. This here. This is new. This was not here last year. This is distinctly new. So there is going to be times where you need to know how much energy is required to break up separate bonds within your organic molecules. This is distinctly something they've added in, and they want you to know about it. So it's really important that you do know about this stuff. How this changes down groups as well. So if you've got like a homologous series of a similar molecule, how does it become, more viscous, stronger, harder to break down, vaporizing point, etc. Atom economy. They've made a much bigger deal of this year because of green chemistry. So you do need to know your atom economy, and you do need to know how that applies into your green chemistry for organic. So these are the two things these two things are pretty much the same. But really important, these are the sort of things we didn't cover. We're not going to cover today, just purely because of time-based sort of restrictions. But really important, these are the things. So you haven't been through this whole topic. Now that we've gone through that stuff, there are some things that we still haven't talked about. So again, there are 20 minutes left. If you want to take a quick break, feel free to go take a quick break, pause and come back. We are quickly going to go through how to approach the exam and how to approach the next couple of months of study, because we've reached that point in time. And it's really important now that we start to make strategies of how we're going to approach the exam, how we're going to get through the exam, just to ensure that we're all on top of this stuff. So really important. In this topic here, what's really important is that you understand that we are now reaching this point where you sort of need to start thinking about this. I don't think you need to start doing practice exams right now, and I'm big on that. I don't think doing practice exams right now is going to be overly useful, and a lot of times you'll feel pressure because some other students will be doing practice exams, and usually the people who've started doing practice exams right now, there's sort of two groups of them. They're either going to be really, really strong students and they're going to do really well, or they're the sort of students who sort of just want to sort of flex on you that they're doing practice exams, and they're going to be like, oh, I'm doing practice exams. Why aren't you doing practice exams? Don't listen to those ones. Those are the students that you don't want to worry about. You don't want to compare yourself to, like they're going to burn themselves out. Don't worry about them. You need to figure out a good time for you to start practice exams. Everyone is individual, and it's really important you understand everyone in year 12 is individual, how they are going to study, when they are going to really start pushing study, when they want to take breaks, all that sort of stuff. You need to understand you're all individuals and you're all going to do things at different times. I realistically think that you sort of have finished sort of 2/3, because realistically you have 3 terms plus a couple of weeks, and realistically you finish most of your topics near like sort of like week 7, 8 of term 3. You don't finish them at the end of term 3. You finish them like week 7 or 8 in term 3. So realistically, you are nearly 3/4 of the way through your content. It is time to start thinking about the exam. As I said, it's not necessarily time to start doing full-blown practice exams, but it is time to start thinking about it. So let's just break up, first of all, how is chemistry structured? Because it's really important to understand how chemistry is structured. If you don't know how chemistry is structured, you're not going to know how to actually go through this stuff. So Unit 3, Unit 4 are worth this amount. Really important. This has got to do with your SACs. Remember, SACs are important. I think they're more important based on reviewing them and discovering where you made mistakes, because they're mini exams. So look at a SAC and review it. Where did I make mistakes? Why did I make those mistakes? SACs, in terms of your marks, far less important. They just give a rank. Marks, it's still important to get a good rank, but your SAC marks will get pushed up or down according to sort of how easy or hard your SAC was for your school, because the exam is the only standardized thing between all the schools. So if your SACs, you're averaging like 95 on your SACs and your whole class is averaging 90, you get in the exam, and then you've got another school and they're all averaging like 70s on their SACs, and then that school that's averaging 70s does better on the exam than the school that averages 95s, it's clear that the people that were doing the 95 SACs, their SACs were a lot easier. And that actually when you standardize the test, they actually did worse than those doing 75s. So then it sort of drags their SAC marks down and drags the SAC marks of that 75 score up. So it's really important to understand that that's how SACs and exams work. So you will have marks sort of moved up and down accordingly. But it's really important in terms of figuring out, where did I make my errors? Why did I make my errors? What do I need to learn? So really important to review them. Your exam is worth 60%, but overall it's worth more than that because it drags up your SAC marks or drags down your SAC marks. It's realistically worth a lot more than 60%. Throughout the year, your end goal should be setting yourself up to do as well in the exam as possible. That's the most important thing. The exam is made up of 120 marks in 150 minutes. I don't know why I've written that. Mins. Apology, everyone. 120 marks in 150 minutes, plus 15 minutes reading. So realistically, you have 165 minutes. This is time to answer questions. Please do not treat this time like, oh, I can't do anything in this time. This is time to answer questions. You can answer questions in this time. You can do multiple choice questions in your head, and remember that question 1 was A, question 2 was C, question 3 was B. You might get 4 of them done. You got 4 less marks to do. You're at 116 marks now in 150 minutes. Please do not waste your reading time. We'll talk about reading time, but don't worry. 30 multiple choice, 90 short answer. This is usually over like 8 to 12 questions. The exam is difficult, but it's also really fair. The chemistry exam is one of the most well-written exams out of all the VCAR exams, and I can attend to that. I've done nearly all of them over my tutoring career. I've done since about, obviously I did my exam in 2018. I would have done all the exams back to like 2012, 2011, and I've done all the exams since. I think the chemistry exam is one of the most fair and well-written exams. There is a large variation in questions. If you're sort of like a middle-of-the-range student, you're aiming for like a 35 to a 40, you are going to find the exam is going to have a lot of questions you find very straightforward, but there are going to be questions on there that you find extremely difficult. because that is why the exam is there to split you all up, and it is really fair. There are questions on there that are absurdly, extremely hard, and there are questions on there that are really straightforward, and that is there to meet the breadth of all the students. So really important. The questions are a little bit segregated. There is distinct overlap, and that is the important thing about chemistry. This is not an English or a general maths exam where the sections are distinctly written out as different sections. You will have overlap. You will have a fuels question that involves redox. You will have an organic question that involves experimental design. These are all going to be integrated, and it's really important to understand. Now, the multiple choice structure as a general rule, most questions in the multiple choice section don't really overlap. That's just a general rule because it's hard to overlap multiple choice. They sort of follow the study design. You'll do a few and you'll realize that kind of follows the study design, starting with fuels and it'll go through to medicinal. They also progressively get harder, sort of. They sort of tend to get harder as they go through, just sort of the way they do. It's just sort of how that sort of works. The short answer structure, again, also follows the general structure of the study design. The first question will be about fuels. The last couple of questions will be about experimental design. But there's overlap. Like, they will overlap topics into each other. They're just the distinct main part of the question will probably be like fuels first. And then it'll be redox. And then it'll be rates and equilibria. And then it'll be electrolysis. But it's all going to overlap, but there will be distinct, like you'll be able to pick, it sort of follows through. The largest question will usually be the last or the second last. It will incorporate a really complex experimental design with another topic, and it will be worth a lot of marks. It will take a lot of writing. I really suggest reading this question in the reading time just so that you know how you're going to approach it. So what should I be doing now? That's the question. I'm going to break this up into 3 features. I think reviewing, exam strategy, and then exam practice are the 3 things you need to be doing. So let's talk about reviewing first, because reviewing doesn't mean you need to be doing practice questions. Reviewing is all about like understanding the concepts before jumping into practice exams, because you need to understand the concepts. Yes, you can do a practice exam knowing 3/4 of the content, and I think that's a big thing. You can start doing practice exams once you know 80% of the content. Yes, you're not going to be able to answer 20% of the questions, but when you're doing old enough exams, it doesn't matter. And when you're doing particularly like doing some company exams early on, also a good thing. But questions are important, but concepts are even more important. You need to get exposure to all the concepts and know how you're going to answer the questions for them and what they're actually asking. So write a list of questions of things you are not sure about, and then make sure you find someone to help you with them, or go and figure it out yourself. Get a textbook, go back to the textbook, read through those things. Ask your friends, your teachers, the internet, etc. You can ask me today in the if you're at the premiere, and you can ask me in that chat of concepts that you really struggle with. These are the things that are important. If you ask these things and you start to understand the concepts, you'll find the questions easier. Really important. Review your SACs. Review where you made errors. That is when you were best at that topic. You will have, like fuels, you're not going to be as good at fuels right now as you were when you did that SAC. Yes, you're going to be better at fuels when you hit the exam because you're going to have reviewed it multiple times. But right now, you're probably weaker at fuels than when you did the SAC. And you made mistakes in the SAC. I'm guaranteeing most people here did not get 100%. So why did you make those mistakes? Where did you make those mistakes? How can you go back and review those mistakes? So focus on points of weakness is a really big thing. Refer to the study design, tick off all the points. Make sure you've ticked off everything in the study design. You go, oh, I know how they would ask about this point. I know how they would ask about this point. I know how they would talk about this. Textbooks and notes. These can provide a very different perspective on topics. So double check. Don't be afraid to go back to your textbook. Textbook questions are terrible for exam study, but textbooks in themselves are really good to go back to and read through if you're forgetting stuff. You can then identify your weaknesses and brush up on it, and sort of just brush up on the concepts and then go and do some exam questions based on those concepts. I really don't suggest doing textbook questions. They're not very good, but textbook content in itself is quite good. Managing time. So now we'll move into 2, exam strategy. So first of all, you need to really work on reviewing and getting your concepts right. That's something you can start doing now. You can start reviewing fuels. You can start reviewing equilibria. You can start reviewing that stuff now. Exam strategy. I think before you start doing exams, you need to sort of think about some strategies of how you're going to approach things. And then you can start to work, if you have multiple different strategies you come up with, when you start doing practice exams, you do each of them and figure out which one works better. But it's really your decision. You can either do all the questions in order or jump around. You just need to figure out what you want to do. The first 30 seconds of writing time, I would really jot down some milestones to keep yourself on track. If that is finish multiple choice by 9:45, should be halfway through extended response or short answer by 10:45, whatever it is. You just need to jot down some milestones. These are just examples. I don't want you to take those as the Bible. You just need to figure out in yourself what are some milestones to keep you on track. Check the clock semi-regularly as you go through and get used to doing this. So if you're doing a practice exam, have your laptop up with the clock up, or have a watch there. Please don't have any other tech there. Try to keep your phone away, all that sort of stuff. Keep yourself not distracted. But have a clock somewhere so you can always just get used to checking it, because that's something you want to do during the exam. You always want to be checking the clock. I know at times that can be a bit anxiety inducing, but it's something you need to get used to because it's really important with your time management. It's always good to then note how far you're progressing through the paper. So then the next part is understanding the question type, and I think this is a really big deal. There are numerous question types and strategies that are really, really important in VCE land. And I'm going to go through one of them today. I'm not going to go through the others, but it's just really important to understand there are distinct question types. And the more you do practice exams, the more you're going to figure out what these are. So when you start doing practice exams, you need to start noting these down. So there's calculation-based MCQs. The biggest thing with this is writing down all you're working out. I know you don't get marks for it, but write it down, because otherwise you'll make errors just doing everything on your calculator, especially those little calculators which you have to use in chemistry. You can't see what you just did. You can go back up, but it's hard. So make sure you write down everything that you do. MCQ elimination methods, so questions that are really wordy, eliminate things. Read through them, highlight what's wrong, get rid of it. It helps you sort of understand where you are. 3, time-based guesstimates. What I mean by that is if you are running out of time, if you can rule out 2 responses and then guess between 2 responses, it's a 50-50 chance. Things like that are a really good thing to use if you struggle with time management. You don't want to do that at the start, but if you're running out of time, you've got 5 multiple choices left, try and rule out things, and then you can make better guesstimates. Short answer diagram drawing, we'll talk about this. Justifying when given the answer. So if you're given the answer, justify. It's always about justification. Justify. Go back to your chemical concepts. Refer to an appropriate chemical concept. Again, this is the exact same thing. If you need to refer to an appropriate chemical concept, refer to it. According to Le Chatelier's principle is something that's really commonly used. Utilizing Faraday's laws, things like that. So referring back to the big chemical concepts that you learnt. Now, let's talk about diagrams. So just quickly, drawing diagrams. Really important. Don't overuse this, but do use this when it's necessary. If you have a really big question, it's worth 5 or 6 marks. A diagram can get you 1 or 2 marks. So put a diagram in there. Yes, you need to write out everything, and you need to refer to the diagram in writing. Please do not just do a diagram and just not write about it. If you are going to use a diagram, say according to the diagram I've put below, please put something like that there. The diagrams look really, really good. So the main goal of the exam is to present your knowledge and understanding to the examiner. That is the main goal of the exam. Yes, you want to get things right, but your main goal of the exam is to say to the examiner, I have done the work. I have done the study. I need a good mark. That's essentially what you're saying to the examiner by answering these questions. Diagrams do this perfectly. So a really good example here is this is a calorimeter. You wouldn't have been through the... it's part of Area Study 1, isn't it? No, it's part of Area Study 1 or Unit 4 Area Study 2. I don't remember. But you will talk about calorimeters. This question is asking you to write, but if you use a diagram, it looks great. Yes, you would write here, but you would refer to the diagram. This would be 1 mark. You've already got 1 of your 2 marks. So then just referring to it and writing a quick sentence about it gets your 2nd mark. So really important, diagrams are a useful tool. Don't overdo it, but do use your diagrams. And then 3rd, exam practice. So as we talked about, your exam strategy, you need to sort of determine which one you want to do and then practice it in the exam practice, and then exam question types you need to observe within exam practice. So realistically, you need to start exam practice. When should I start? Look, as I said, this is a difficult question. I think it's really important to review the content first and be comfortable with it. I also think, as I said, you need to be 75 to 80%, I would say, through the content to really be comfortable. I would say you must have completed Area Study 1 for Unit 4, I think at a minimum, to do this, to start doing papers. And when you start doing papers, please do not do the newer VCAR papers. 2017, 18 probably to 2024 papers, do not touch them, the VCAR ones. Do not touch them until, I'm going to say, after the term 4 holidays. They mustn't be touched until after the term 4 holidays, unless your school wants you to do a specific one. That's okay. Do not touch them until after the term 4 holidays, please. I would say at a minimum, you need to have at least done one practice exam under exam conditions before the term 3-4 holidays. So if you want to start off by doing these things open book and in chunks, go for it. And do 1 or 2 of them open book and just get a feel of how exams work, go for it. But I think before the 3-4 holidays, so before the holidays that are in September, you need to have at least done one practice exam under exam conditions. You've sat there for the 2.5 hours plus 15 minutes reading and done the whole exam. That's vitally important. Use a data booklet when you're doing them. Like, do them as you would in an exam. And I think the best way to start off is to do some new accompanying exams. Like, maybe do some old VCAR ones, but there's going to be a lot of content that's not relevant because area studies have changed. Like, you can do like a 2014 one or something like that. But do some new accompany ones. Like, ask your teacher. They'll have company exams. All teachers will have, and all schools will buy some exams from some companies. Get maybe your 2022, 2021, have a go at that. Yes, they're not going to be the exact perfect because you have a new study design in 2024, but the reality is doing some of those is still going to be very similar. And as I said, VCAR is the golden standard. Please try and keep these until term 4. Please do not. And how many? Well, it's really important that it's quality over quantity. This is a graph you will see when people talk about knowledge. You will plateau. You will reach a point where it's really hard to get any further. It's natural. But it's really important that the number of practice exams doesn't necessarily give you value. You are it's quality over quantity. Really important. Quality over quantity. And then also really important, you need to approach exams the way you approach exams is probably the most important. So how do you make practice exams count? Use the reading time. Reenact the exam conditions. Correct them yourself. Please do not give your teacher an uncorrected exam unless you are literally doing one in a class and then they're going to correct it for you. Please do not do that. Always correct it yourself. You learn far more by correcting something yourself. You do not learn from giving it to your teacher and then just looking at the 3 things that they wrote down. Please do not do that. Correct them yourself. And reflect on mistakes. Review. Doing another exam straight after one exam without reviewing where your mistakes were is just pointless. Review your mistakes. That's something you need to get in the habit of. But most importantly, look after yourself. I've probably drilled a bunch of things in you and you're all getting all scared about it, but please don't. Please look after yourself. The reality is, over the next sort of 3.5 months, you really need to start getting into good habits. So get lots of sleep, eat well, exercise regularly, keep up your hobbies. Like, if your hobby is literally something like, playing a video game or going and having a hit of tennis, allocate yourself half an hour of that, a day or something. Allocate your time to do that. Like, if that's your hobby, if you love reading, allocate yourself, 40 minutes a day or something and do that. Like, keep up your hobbies. People will say to you, oh, but you're not studying, you shouldn't be wasting your time. It's really important to keep those things up because that's what's going to make you feel comfortable. And when you get to the exam, you're going to feel so much better. Honestly, if you're healthy for the exam, you're going to do so much better. Other than that, good luck. That is it for our July lecture. We will be back in September with some more content. We'll probably review Area Study 2 for Unit 4 and then do some more exam stuff. Other than that, check out all our 8-out note stuff and I will see you at the next lecture.